Welcome to bmac.math tutorial. Subscribe to our channel and hit the bell icon for freshly brewed content.
Hi, this is a question from CSI and NET 2019 December from metric spaces. This is a question from part C. Here we are given a compact metric space xd and a continuous function defined from x to itself, satisfying the condition infimum of n belonging to the set of natural numbers d of t to the power nx, t to the power ny not equals to 0 for every x not equals to y in capital X. Now t to the power n is nothing but the composition of the function t n times. And we will check each of the conditions 1, 2, 3, 4 separately. But we will start with the definition of metric spaces. So metric space is a two-tuple xd where x is a non-empty set and d is a function known as the distance function or the metric function that satisfies three conditions. The first condition is the non-negativity condition, and which says that d of xy is always greater or equals to 0 and d of xy is equals to 0 if and only if x is equals to y. We can also say that if x is not equals to y, then d of xy is always strictly greater than 0 and vice versa. Second condition is the symmetry condition, which says that d of xy is equals to d of yx, and the third condition is the triangle inequality, which is satisfied for any 3 points x, y, z in capital X. Now xd is also a compact metric space, and by a compact metric space we mean that for any for any open cover of X, there always exists a finite subcover. So we also know that any compact metric space is always closed and bounded, but the converse need not be true. And as a counterexample, we can consider an infinite set X along with the discrete metric defined on X. So if we consider the open cover as the set of all singletons in the infinite set X, then it clearly does not have any finite subcover. So we will start with the first condition. We are given that for any x not equals to y in capital X, infimum of d t to the power nx, t to the power ny is always not equals to 0. So for any natural number k, we will always have this inequality, and putting the value of k is equals to 1, we will get this. Now since d is a non-negative function, so 1 implies that d of tx ty is strictly greater than 0. Now by the first condition of the metric function, we can say that t of x is not equals to t of y. So we started with two distinct points x not equals to y in capital X, and we have got t of x is not equals to t of y, and hence the function t is on 1, 1. That is injective. Thus option 1 is true and resultantly option 2 is false. So option 1 is true and option 2 is false. Option 3 says that image of t is closed in X. Now t is a continuous function, and we know that the continuous image of a compact set is always compact. So t of X is compact. Also we know that any compact set is always closed and bounded, so t of x is closed and bounded. Thus tx is closed and option 3 is true. So option 3 is true. And option 4, we are given that if x is finite, then t is on 2. So we also know that if any set is finite, then any function from x to itself is injective or 1, 1 if and only if it is onto or surjective. So we have also already seen from option 1 that t is an injective function from x to itself. Now if x is finite, then t is an injective function from a finite set to itself, and hence t has to be onto or surjective. Thus option 4 is also correct, and thus our correct options are 1, 3 and 4. So thanks for watching.